This is Math 280, Multivariable Calculus. I'm Professor Wheatley. Today's topic is arc length and unit tangent vector. The first of three sections on some differential geometry from a very elementary perspective. So let's talk about arc length to start with. Arc length actually is a topic which is familiar to us from Calc 2. We spent some time there developing it as one of the applications of the integral, and so luckily a lot of our hard work has been done. We're not going to repeat that process of chopping up things into intervals again. We'll use that to just kind of add another term on for a 3D. So where do we want to start? Let's start with a smooth space curve. Space curve R of t, and smooth, no gaps, no sharp corners. So we want everybody to be continuous and infinitely differentiable. So we need a nice smooth space curve. And so here's an example of a beautiful smooth space curve there. And you can imagine that in 3D. OK, so pick a base point. Doesn't really matter where you go. So say there's our base point in this, right? And so I'll call it 0, and really what I'm doing here is just basically working like on a number line. My base point is something, and from it there are other values around it. How can I talk about arc length? I can locate other points on R of t by giving their directed distance from the base point, just like a number line, right? I mean, a number line, 0 is the base point, and 1 is 1 unit in the positive direction. -1 is a unit in the negative direction. Same idea. So maybe this guy is 1 unit away in the negative direction, and maybe this guy over here is 2 units away in the negative direction, so it's 2 behind the base point, and 1 ahead of the base point, and 2 ahead of the base point, right? So this is not any kind of a functional value here. This is 1 unit away from the base point in some measurement we're doing here, some measurement system, right? And we can use this to measure. And actually, I've missed something here. I wanted to say distance s, so I'm going to call the distance s. In other words, this is s equals 1 and s equals 2, right? So this is distance s. And I can use this to measure length. So I can use s to measure length along space curve. Right. OK, so let's think back a minute here to Calc 2. So recall, say we had a smooth plane curve C, and say C was defined parametrically, right? So maybe C crosses itself and things like that. Not necessarily a function, just a nice smooth plane curve, no gaps, no sharp corners, nothing like that, right? Over an interval t between a and b, right? So there's the interval. And we could define the length of this curve to be an integral, right? In particular, it was the integral, definite integral a to b of dx dt squared plus dy dt squared, and then dt out there. Right, so remember, that was one of the things that you spent time doing in Calc 2. We will not reinvent the wheel and recreate that, but that is the formula for length of a smooth plane curve. Right? So what do we do for a smooth space curve? Well, unsurprisingly, this formula plus a third term. So when you have something in 3 dimensions, we don't need to reinvent the wheel. We just go ahead and stick in a third piece. So if we have a smooth space curve R of t, and say it is some components x of ti ytj, ztk, like that. And again, suppose time is running between a and b, right? Then the length L is definite integral a to b dx dt squared, dy dt squared, and then the only thing we change, the addition of a dz dt squared, and then dt. So nothing spectacular. You could certainly derive this in the exact same fashion you derived this equation for the 2D case. Okay. As a shorthand way, we recognize this as something else. Right? In fact, this is the length of the derivative, right? The derivative is x prime ti plus y prime tj plus z prime t k, and square those guys, sum them, take the root. That is the length of that velocity vector. So this is the length of velocity, right? And we can certainly see that still L will always be greater than or equal to 0. We want that. This s over here, this s can be directed, or it is directed. It can be positive or negative. L is a length. Length is not a negative quantity. In other words, this may take into account which way from the base point you're going. The length of a space curve has no regard for which way you trace it. It is length going this way, the same as length going that way. It doesn't matter which way you go. It's always a non-negative quantity. All right, so a few considerations here. Right? Another way of saying length of velocity is speed, right? Velocity is a directed quantity. It's vector. Speed is a scalar quantity, right? It's got no direction to it, so this is speed, right? What is another way of saying speed? It is the rate of change of distance traveled per unit of time. Right? Rate of change of distance traveled per unit of time. And this doesn't take into regard what direction distance was. Doesn't matter, right? Velocity takes it into account, right? So, furthermore, makes sense if I integrate speed over a time interval, I get total distance. And think about this for a minute. If I integrate velocity, what I'm getting is a net change in position, right? Think back to the single variable calculus, right? In other words, if I begin here and I move this way, I've certainly moved some, but then I turn around and I walk back, my net change in position is 0, right? So in other words, I haven't moved as far as velocity is concerned. But if I integrate the absolute value of that function, then I count this twice. Now I've moved one chalkboard length, two chalkboard lengths. It's different. See, I mean, with velocity, I haven't moved at all. My position change is 0. With speed, my position change is 2 chalkboard units. I've gone that far, right? So it's this that I want to integrate, not velocity. Velocity will give me a net change. Speed will give me total distance traveled. I don't care whether or not I go one way or the other. I do want to be careful, though. I don't want to go along a curve and go back over a point again, because then this will count it again, and I don't want that. I mean, I don't want to traverse the same section of the curve twice and count it twice in arc length. That's bad. I wanted to count it once, so make sure I don't traverse things more than once. But this does make sense from an integration standpoint. Okay. Well, let's look at an example. Calculation-wise, if you recall from Calc 2, arc length integrals were often hard. I mean, you had enough integrals that were very hard to do most times, and nothing's changed in Calc 3. most times these integrals are undoable by exact methods. So we're going to use ones that are sort of nice and easy. But a lot of times you're forced to resort to numerical methods to get these approximate answers here. So here's a particle. It is traveling along some path, and let's give it a nice, easy helical path. 3 cosine ti plus 3 sine tj and 2tk. So that's a nice helix. Remember that from 13.1 or previous vector valued functions, yeah. Travel along that path. My question is, how far does travel from t equals 0 to t equals 2 pi seconds? How far does it travel? So, AKA, what is the arc length of that section of the curve? Okay, so what do we need? Well, velocity for one thing, because we're integrating length of velocity. So velocity minus 3 sine t I, 3 cosine t j plus 2k, right? And then my length of velocity, right, ends up being, what, 9 sine squared t plus 9 cosine squared t plus 4, right? And so we see that with a helix, this is nice and easy to do. Normally, this would be difficult to integrate this. But this is simple. You can factor out a 9 here and get sine squared plus cosine squared. That's 1. So this winds up just being root 13. Right? So this is, again, has a constant length. And remember, that's actually what characterizes a helix, is this kind of form. You have a circle in the xy plane and a linear term on the third axis, or really a circle in one of the coordinate planes and a linear term in the other axis. It's the characterizing property of a helix. It has constant length at every point, or its velocity does at least, constant length at every point. So when I look for length, right, what I want here is 0 to 2 pi, right, root 13 dt. This is straightforward. That's 13t from 0 to 2 pi. We'll wind up with root 13 2 pi. I guess I used pi on my notes. It doesn't matter, though. So this is whatever it is. This is units along the curve. And that should be about 22.6, theoretically, if this is all right. Yeah. So there you go. There is how far it's traversed from this time to that time. In fact, this is one full rotation around the helix. You're back to where you started again when you go around 2 pi. So wherever you began here, and then you rotated around the helix, and now you're back to the same position in the xy plane, only you're 2 pi, or you're 4 pi higher on the axis. Okay, so there's an example. Why use arc length? It comes into play quite a bit down the road, but for now, let's try to give some notion of why this is helpful. It's a nice thing to know in general. I mean, length of a curve is as good to know as anything else about it, but it's more than that. There's a useful reason for why we're doing it. So why arc length? The big reason for us is, or one big reason at least, it's constant regardless of parameterization. So regardless of the curve's parameterization, arc length remains constant. Example here is good to see. Suppose I had the function, or the space curve, ti, t squared j, t cubed k, and I'm fixing time between 1 and 2. So there's that. How could I reparameterize this? Well, take a look. Suppose that I made a substitution. So I made a substitution. Suppose I let u equal natural log of t, right? And so that means that e to the u is t, right? E to the u is t. Then this parameterization up here becomes now parameterized in terms of u, and it's e to the u I, right? Plus e to the 2u j plus e to the 3u k, right? And the time interval changes too. It used to be 1 to 2. Now it begins at ln of 1, which is 0, and goes to ln of 2. So now our new time interval is from 0 to natural log 2. But one parameterized by t, one by u, different time intervals, same arc length. So these guys have the same arc length. These have the same arc length. It just happens to be that this one is traced faster. This one takes 1 time unit to trace. This one takes a natural log of 2 time units to trace. Yes, so the curve is traced. Actually, I've said this. Yes, so the curve is traced faster in the first case there. So they have the same arc length. Okay, so that's one reason why to use arc length. Again, arc length is a non-negative quantity. Arc length is a directed distance. Be a little bit careful with that. So let me talk about the arc length parameter here briefly. Talk about the arc length parameter here briefly. Length parameter. For a curve, it's a function of time defined as follows. Function of time defined as follows. Again, you got to pick a base point. Doesn't matter where it is, but it's got to be some base time, t naught. T equals 0 tends to work well usually for this, if you can do it. And then whatever the functional value is at that point. Right? Then any value of t determines a point p of t. That. So some other point. So in other words, the t naught determines this point, and everybody else, somebody else, right? Maybe even the same point if you come back around, but you've still traveled a distance, right? So you're someplace else on the curve for every value of t. P of t has directed distance s of t. This should be s of t from P of t naught. In other words, here's the picture. So say you're carrying on in your space curve in that direction. Say you're orienting yourself like this. Maybe there's the base point, right? And here's somebody else, P of t, right? Right? That highlighted black line there, that's s of t, right? So we see that arc length depends on our choice of time, and also our choice of base point too. The base point makes a difference. That's why you have to be very clear what you're using there. And generally, if you can use 0, you may as well. There's no reason not to, unless you've got something else that you need to do. But there is your arc length. And we can see that t can either be greater than t0, in which case you're proceeding in the direction of the arrows, or less than. In other words, if I picked a point down here, right, I'd be going against the flow of the space curve. I'd be going to a t less than t0, something in reverse. Maybe if this is 0, I'd be at t equals -1 down here, and this is t equals 1. So 2 cases here. If t is greater than t0, s of t literally is length. It's the length of the curve from p of t0 to p of t. In other words, if you're carrying along in the direction of the curve's orientation, the direction of the arrows, s of t is the length. If you're not carrying on that direction, if you're going reverse, in other words, now you're going against the arrows, so you're proceeding this way, for example, t less than t0, then s of t is the negative of the length of the curve. From p of t0 to p of t. So this arc length parameter can be negative. The length of the curve is positive. L is the integral of the length of the derivative. This arc length parameter depends on both the choice of the base point and also the choice of the value of t, in other words, the orientation of the curve. Okay? It's not a big deal, but it is important to make note of that. So what is this telling us? Arc length s of t is then this integral. Right? In other words, it's the integral from t0 to t, and if this is less than that, we have to put a negative in front of that, right, of this length term. And I'm using tau here. I'm not using dt because t is my upper limit here. So this is just some vacuous variable here, just a substitute variable. It doesn't matter. But I can't use t here because I'm integrating with respect to the upper limit t. It doesn't work. This is just something substitutionary here. I could have put anything I wanted. I could put a gamma or whatever I wanted to have there to hold that place, right? So what do we know about this now? Think back to FTC1 from single variable calculus, right? We have a fixed point, a variable upper limit, right? What does FTC1 say? It says integrate the derivative and get back to the original function again, right? Integrate the derivative, get back to the original function. So this says that, I'm saying that wrong. I'm thinking FTC2. FTC1 says differentiate the integral, get back to the original function, excuse me. So let me say that again. FTC1 says if you differentiate the integral, you are back to the original function, right? Differentiate the integral back to original function. And so that means that the derivative here is just the function being integrated, which is v of t, right? So the derivative here is the function being integrated. S prime equals v of t. And that makes sense. What is S prime? S prime is the rate of change of arc length. So rate of change of distance traveled with respect to time is speed, right? Rate of change of distance traveled with respect to time is speed. That makes perfect sense. So it's kind of a way of getting around arc length being a directed quantity, but it's unavoidable. But this is helpful to have this. So there's arc length. Let me talk about unit tangent vector now. Get rid of this we'll come back to arc length down the road a little bit. We'll talk about some other things. I want to talk about unit tangent vector. Okay, so over the next 3 sections, we'll talk about 3 different unit vectors which make up a moving frame of reference for an object moving in actual motion in 3 space. The first one of these will be t, which is unit tangent. So let's talk about that here. The velocity vector is another word for r prime. So here's position, and its derivative is velocity, right? And we know that velocity is tangent to the curve at every t. That's property derivative. Derivative is a tangent vector to the curve at every t, right? It is not necessarily a unit, certainly, but if you divide by its length, if you normalize, you get a unit vector. So if I take v of t and divide it by its length, what do I get? I get this thing I call capital T of t, right? Still dependent on little t, but this is the unit tangent vector in the direction of v at time t, right? And so remember that the tangent line is not only tangent, but also points in the direction that the curve is moving, right? So it's the tangent line that gives the inclination of the curve to go forward. So this points in the, let me say it this way, it points in the direction of motion, or the forward direction of the curve, right, at time t. Depends on t because, well, v depends on t, right? But it is a unit, and it points in the direction of motion of the curve at time t. All right, let's try a little example here. Again, it's a little hard to see how this works yet because we don't have the other 2 vectors that make up the frame, but we will see. So let's find t of t for our particle in the previous example. So we had 3 cosine ti, 3 sine tj, 2tk. So this guy was the same curve from the last time, and now I want his unit tangent at every point. All right, so we already know v. We said that last time, -3 sine, 3 cosine, 2k, all right? The length of v, we know that's root 13. Here is where things can get pretty ugly. If this was not something nice, this length could be an ugly function of t. And that could make this pretty ugly over here. But here we have something very nice. Helix has constant length in terms of its derivative. So what's t of t? -3 sine t over root 13, right? So I'm just dividing through component by component. Okay. And this thing is a unit vector tangent to the curve at every point t, which will point in the forward direction, in the direction of motion with increasing t at every point. Okay, that's it.